Is it?
Yes. అబ్బో ఇంకో షోల్డర్ రావట్లేదు. అబ్బో coordination compounds model. So here we are going to discuss first nomenclature, next Werner's theory, next EAN concept. Shiva, right side. ఓ పక్కన రాయి మళ్ళీ EAN, next isomerism, VBT, next CFT, next organometallic compounds, and the uses from text. Okay, a textbook lo uses to చదువుకోవాలి ఇక.
Okay, sir.
ఇవి డిస్కషన్ మనకి చాలా ఇంపార్టెంట్ పాయింట్స్ దీంట్లో నుంచి మనకి. నౌ nomenclature. Listen here. Shiva, please respond continuously. Okay.
Yes, sir. Yes, sir.
So coordination compounds. These coordination compounds, what are these coordination compounds? In old days, we have some compounds like alum. Alum, its formula is K2SO4, Al2SO4 thrice, 24H2. Next, more such. So I think in practical, the salt name you well know. More salt. That is FeSO4, ammonium sulfate, 6H2O. Carbonate. Nothing but KCl, MgCl2, 6H2O. These are all salts, my dear. So this is one salt, this is another salt. Here also, this is one salt, this is another salt. That means these are the compounds having two salts with water molecules. All these are nothing but double salts. So no doubt all these are solids. These solids unite, these solids containing two salts along with water molecules. These are hydrated salts. Two salts are there. That's why this is called as double salts. Okay. So in solid state only, all these ions unitedly one end. But when these substances are dissolved in water, for example, if this is dissolved in water, it breaks down into K plus ion, Cl minus ion, Mg plus 2 ion, Cl minus ions. Okay. For example, if this is dissolved in water, that gives Fe plus 2 ions, SO4 minus 2 ions, NaH4 plus ions, SO4 minus 2 ions. For example, this one is dissolved in water, that gives K plus ions, SO4 minus 2 ions, Al plus 3 ions, SO4 minus 2 ions. That means in water, in solution phase, so these are break down into respective ions and gives corresponding test. That means if you want to test this aqua solution, that responds K plus ion test, Mg plus 2 ions test, so and also Cl minus ions test. That means in solid state only these are unite, but in liquid state they are individual. Am I correct, Shiva? Did you understand? Solid state lo maatrame కలిసి ఉన్నాయి. But aqueous state, solution state, these are in ionic form, their own individualities are there. Okay.
Yes,
So
sir.
like this here also. So this type of substances, no doubt these are soluble in water. In solution, they have individual tests, not collective property. No, they don't behave like collectively, like here. Here individuality is there.
Yes.
So that type of salts are called as double salts. But at that time, scientists well known that some type of compound there is COCl3, 6NH3. Okay. Next, CrCN thrice. Just a minute. CrCl3, 6H2O. FeCl3, 6H2O. Like this, here also some molecules are there. Shiva. Okay. So, like this, these compounds, scientists are also expected. No doubt, these are also solids. So they feel like that, they're like just like this. When they dissolved in water, they expected CO plus 3 ions and Cl minus ions because it is ammonia. Ammonia, when dissolved in water, that gives NH4 plus ion. So those scientists expected these ions from this salted, but practically only Cl minus ion is identified, but not CO plus 3 and ammonium ion. That means all the species cannot give respect to ions, but here all are giving respect to ions, but here are not any. See here also Cr plus 3 expected, Cl minus expected. Okay, water is not there, but only Cl plus minus observed, but not Cr plus 3. Here also Fe plus 3 expected, Cl minus expected. Here Cl minus accepted, but Fe plus 3 is not observed there. That means in solid state these are unite, but in liquid phase also this one and this one is combinations, united combinations exist. Only this one is individually existed. That is why this test is applicable. This is the positive test, but not these two.
Yes, sir.
Okay, that means these two are same type or different type? Tell me.
Different types.
Different types. Why these salts behaves like that? So scientists at that time they don't know. So that's why they are giving some complexity is there. In this salts, some complexity is there. That is why these salts they named as complex salts. Later, these complex salts are considered as coordination compounds.
Sir, in water or liquid solids, sir?
In water are also solid. Solid phase they are unite. Liquid phase also unite.
Yes,
Only
sir.
a few are breakdown. But here all are breakdown.
Yes, sir.
Okay.
Okay.
So this is coordination compounds or complex compounds. So this is our chapter. Okay. This is salt. This is salt. But here only solid state they are unite. Here solid state no doubt unite. But these are breakdown into corresponding ions completely in active state. But these are not completely breakdown into corresponding ions. A few are breakdown, but others are not breakdown. Okay.
Yes,
So
sir.
that is why some complexity is there. That is why this type of compounds are called as complex salts, are also called as coordination compounds. Okay.
Okay, sir.
Now these two are no doubt molecular substances. Molecular substances break down into two types, double salts and complex salts. So now we are in complex salts. How these complexes are formed? What is the difficulty base? Why these are not completely ionized? Which type of bonds are there? So that was clearly explained on the basis of Werner's theory. Later we will discuss. So now, what are these complexes? How many types of complexes are there? How those complexes are I explained? Okay, all
Yes.
those are here we are going to discuss. First of all, we are going to discuss Werner's coordination theory. After that, we are going to learn that is nomenclature of the compounds. First of all, Werner's coordination theory. Why this complex, these substances are not break down into corresponding ions. So that is explained on the basis of Werner's theory. Werner's theory. This explains formation of a complex. Werner's theory clearly explains the formation of complex cell. Okay, what is this Werner's theory? Werner, a scientist. So, boys, after knowing complex compounds, it is difficult to the scientists why those substances are not soluble completely. They don't know it. Even after knowing 100 years. Even after knowing 100 years, so scientists didn't understand why those substances are not break down into corresponding ions. Okay, so at that time, this Werner clearly explains after 100 years of knowing the compounds, clearly explains by taking some theoretical concepts. So why and why not? That is clearly explained. Why Cl minus ion only break down into ions? Why not cobalt and ammonia break down into ions? So clearly explained on the basis of his theory, and that theory is called as Werner's theory. See here, let us take an example. COCl3 6NH3, my dear. This is one of the complexes. Like this, I'm replacing COCl3, 5NH3 also exists. COCl3, 4NH3 exists. COCl3, 3NH3 also exists. Okay, these are the different salts from this complex set. Okay, na Shiva? COCl3, 6NH3, 5NH3, 4NH3, 3NH3. Clear?
Yes, sir. Clear, sir.
Okay, now why these are not break down into corresponding ions? So for that, he explained, see, every complex has central metal atom or ion. That should be D block metal. Mostly D block metal. Okay, right? First point, every complex has central metal atom or ion. Mostly D block metal. Mostly D block metal. Okay,
Yes, yes,
that
sir.
is the first point he gave to us. Next, that metal atom ion has two types of valence. The central metal atom or ion has two types of valency. It is point number 2. What are those? These two types of valency. That is, one is primary valency, and the second one is secondary valency. Okay, now
Yes, sir.
every metal has two types of valency. One is primary valency, another one is secondary valency. Primary valency is nothing but this is satisfied with primary valence is satisfied with actually primary valency equals to oxidation state of metal. Primary valency equals to oxidation state of metal. Okay, so for example, in this complex, cobalt has +3 oxidation states. Therefore, primary valence is equal to 3. In all these cases, cobalt has +3. Okay, secondary valency is equal to, it is equals to coordination number of metal ion. Coordination number of metal. What is that coordination number? Later we will discuss. So primary valency equals to the oxidation states. Secondary valency equal to the coordination number. That is very, very important. Okay, now that means metal has oxidation state always positive mostly. Therefore, positive oxidation state is possible for primary valency. It is some units only. Later we will discuss what is that coordination number. Okay. Therefore, he gave a suggestion that is metal ion along with, see here, this coordination number satisfied by ligands. Coordination number satisfied by ligands. What are these ligands? Ligands are nothing but those are species having at least one lone pair. This species made here either positive, neutral, or negative. This is positive one, or negative one, or neutral one, whatever it may be. But it has lone pair that can donate its lone pair to the metal atom or metal ion. This one is called as ligand. Clear?
Yes, sir.
Any species, whether it is positive, negative, or neutral, whatever it may be, if it has at least one lone pair that can denote it to metal atom or metal ion, that species is called as ligand. Clear?
Yes,
This
sir.
bond,
Clear.
because here this ligand donates this lone pair to this one. This is electron pair donor. This is electron pair acceptor. Okay now. Electron pair donor are nothing but Lewis base. Electron pair acceptor is nothing but Lewis acid. That means in complex compounds, metal atom or metal ion acts as Lewis acid. That ligand acts as Lewis base. There should be a coordinate covalent bond between ligand and metal. Ligand to metal. There should be a coordinate covalent bond between ligand to metal ending. So, because coordinate covalent bond exists between metal and ligand, that compounds are called as coordination compounds. There is a coordinate covalent bond. There is a dative bond. Okay, that is why these compounds are called as coordination compounds. That is why this is called as coordination compounds. Clear?
Yes, sir.
Very, very important. Next. So every atom metal has this one. So how many coordinate covalent bonds? See here, my answer is the number of coordination bonds present around a metal in the complex is called coordination number. The number of coordination bonds present around a metal or metal ion in the complex is called as coordination number. That coordination number is nothing but secondary valence. Is there any doubt up to now?
No, sir.
So metal has coordinate covalent bond. That number of coordinate covalent bonds present around metal atom is present as coordination number. That coordination number is nothing but secondary valency. Okay, this oxidation stage, this is satisfied by. See here, metal has positive one satisfied by negative ions. Am I correct? My dear, here metal ion has plus n charge. Negative ion, that negative ion has negative. That is, for example, X or something else, A minus. Negative ions. This positive is satisfied with this negative ion. So here is metal when that negative ion, there is ionic bond exists between metal ion and these negative ions. There is ionic bond, which is nothing but electrostatic bond. Which is nothing but electrostatic bond. Okay, now.
Yes, sir.
So that means Metal ion and negative ions are attracted by ionic bond. So this ionic bond, when dissolved in water, this ionic bond, when dissolved in water, gives respective ions. That means break down into respective ions. But this coordinate covalent bonds not break down into ions. That is coordinate covalent bond cannot break down into respective ions, but ionic bond break down into ions when it is dissolved in water. Clear, Shiva? That means metal has two types of bonds. There is nothing but two types of valency. One is coordinate covalent bond, one is ionic bond. Those species which are bonded with coordinate covalent bond cannot break down into ions, but those can be bonded with ionic bond can be break down into respective ions. Okay, na? So that is why some fractions, some parties break down into ions, some fractions not break down into ions when they are dissolved in water. Okay. Now, based on these concepts, he gave a structural formula for complexes. That means, so metal atom with ligands. So between metal atom and ligand, there is a coordinate covalent bond. So that is inside the square brackets. That means it is not break down into respective ions. Those which are involved in breaking down, that means which are bonded with ionic bonds, are outside the square bracket. Outside the square bracket, inside the square bracket, along with metal. Metal and ligands inside the square bracket, ordinary ions outside the square bracket. Clear?
Yes, sir. A point of the sir, please. Third point.
Here, see here, metal bonded with coordinate covalent bond with ligand, correct or wrong?
Yes, sir.
Okay, so those are bonded with coordinate covalent bond with metal. Those species within the square bracket,
Yes.
because it is not breakdown. Okay,
Okay, sir.
next, those species which are bonded with ionic bonds, metal with ionic bonds with A, clear?
Yes, sir.
That is outside the square bracket. Metal with A, metal with ligand. Here is a bond, here is a bond. This is coordinate covalent bond, this is ionic bonds. So with ionic bond outside the square bracket, with the coordinate covalent bond inside the square bracket along with metal. Now clear?
Yes, sir. Clear, sir.
Okay.
Yes, sir.
Now outside the square bracket, there is the primary valency. Inside the square bracket satisfies secondary valency. Correct or wrong?
Yes, sir.
Okay. So this is the Werner formula for these complexes. Let us observe. Let us observe. So now these formulas we can write in Werner's way. Werner's way. How is that? See here. So here is metal. These 6 ammonias bonded with coordinate covalent bonds and 3 chlorines outside. Now how many primary valency, how many secondary valency, my dear? Primary valency. That means each ammonia gives 1 coordinate covalent bond. 6 ammonia gives 6 coordinate covalent bonds. Therefore, coordination number is equal to 6. Here, cobalt has +3 oxygen states. Because it is +3, 3 chlorines are 3 minus 1. That is satisfied. Therefore, oxidation state is equal to +3. Therefore, which is equal to primary valency, which is equal to secondary valency. Clear?
Yes, sir.
So here primary valency 3, secondary valency 2. See my dear, primary valency of any metal ion, primary valency, it is equal to the oxidation state. Secondary valency, that is equal to coordination number. It is almost all fixed for a metal. Secondary valency fixed for a metal only, always. Clear up. For example, cobalt has CO+3 has coordination number always 6. Don't change that value. Coordination number of CO+3 is always 6. See here. Here, 5 ammonia boys. Shiva. So cobalt, no doubt, with 5 ammonia, that means how many coordinate covalent bonds are formed?
5, sir.
5. But number of coordinates number of the cobalt is 6. Satisfied or not?
No, sir.
No, that is why one chlorine also inside. This chlorine also acts as donate electron pair to the coordinate cobalt. Now coordinate number is how much? 5 plus 1. 6. How many chlorines remaining? How many chlorines
2
remain?
chlorine.
2 chlorines outside. Okay now. But cobalt oxygen state plus 3 because this one minus 1, this 2 are minus 2. Overall minus 3, this is plus 3. New ammonia is clear.
Yes, sir.
Now here, cobalt, 4 ammonias, NaH3, 4 times. But cobalt coordination number always 6. So 2 more required. That's why 2 chlorines inside the square bracket. Now 1 chlorine outside. Correct or wrong? Tell
Yes,
me.
sir. Yes, sir.
Now write down yourself that last one.
Sir, all will be inside this last one.
All will be in the inside, no outside. Okay.
Yes, sir.
CO, NaH3, 3 times Cl3. It is the complex. Okay. Now see here. The number of chlorine atoms inside the square bracket satisfies both primary valency as well as secondary valency. Clear?
Yes, sir.
So here 1 chlorine inside. That means this chlorine satisfies because it is inside the square bracket. It satisfies no doubt secondary valency and also satisfies its oxidation state because it has minus 1. Okay, that means this chlorine satisfies both primary valency as well as secondary valency.
Yes, sir.
Next, here these 2 chlorines satisfies both primary valency and secondary valency. Here 3 chlorines satisfies both primary valency and secondary valency. These 2 chlorines, tell me, my dear, are these satisfies secondary valency or not?
No, sir.
No, only satisfies primary valency.
Yes.
Okay, na? So those chlorines which are inside the square bracket satisfies only satisfies both primary and secondary valency. Outside the square bracket only primary valency. Okay, na? Chlorines particularly.
Yes, sir.
Clear? Okay.
Yes, sir.
Now, according to Werner, see here, metal has 2 types of valency, no doubt. See here, it is metal. It has 2 types of valency, primary valency and secondary valency. Primary valency is this ionizable or not ionizable? Break down into ions or not? Primary valency break down into ions or not?
Yes, sir. Yes, sir.
Yes, that is right. Primary valency is nothing but ionizable valency. Primary valency is nothing but ionizable valency. Clear? Next, secondary valency break down into ions or not?
No, sir.
No, it is non-ionizable valency. Secondary valency is nothing but non-ionizable valency. Clear? Ionizable valency and non-ionizable valency. While writing the structures, this ionizable valency is indicated with dotted lines. Wherever dotted lines are there in the structures, that is ionizable valency. These non-ionizable valency is indicated with solid lines, thick lines, while drawing the structures. Non-ionizable valency represented with solid lines and ionizable valency represented with dotted lines. Clear? I'm drawing
Clear.
structures for those complexes. I'm drawing structures for example, if a species can satisfy both primary valency and secondary valency, then you can apply both dotted lines and thick lines for that particular species. Okay.
Yes, sir.
Now we can write structures for those complexes. Just a minute. See here, Shiva. Now, what are those complexes? CO, Cl3, 6NH3. CO, Cl3, 5NH3. CO, Cl3, 4NH3. CO, Cl3, 3NH3. These are the complexes. Now write down Werner's way. Write the formulas. Tell me, Shiva, within the bracket, what are those species are available?
Cobalt and
Cobalt
CO,
and NH3,
NH3 taken 3, Cl3.
6 times outside Cl3, correct?
Cl3.
yes, sir.
Next, here CO,
Cobalt,
NH3,
NH3 5 times.
5 times Cl, Cl2. Next, here CO, NH3, 4 times
What else?
Cl2,
Cl.
Cl. Now, here is CO, NH3, 3 times Cl3. Okay, now, see, my dear, when it is dissolved in water, what are those ions? So all these box ion plus 3Cl minus ions. Because it is 3Cl minus ions, this box has plus 3. Now satisfied or not?
Yes, sir.
So now this box, inside the box, what are those available? CO, NH3 6 times. Clear?
Sir, total number of ions is 4, sir.
Total number of ions. So it is box ion plus 3 ions. Total 4 ions are possible.
Okay, sir.
Okay. Now here, when it is dissolved in water, now this box ion, that is CO, NH3, 5 times Cl plus 2 ion, 2 Cl minus ions. Correct or wrong? Because 2 Cl minus this box ion plus 2. Now it is totally neutralized. Shiva.
Yes, sir.
Now how many total ions?
4, sir. 3.
Number of ions. How much? 3 only. Box ion plus 2 Cl minus ions. Okay, now. Next, when it is dissolved in water, this box CO, NH3, 4 times Cl2 plus ion, Cl minus ion. Now, total number of ions. How many? 2 ions only. Total ions 2. Okay, now. Next, when it is dissolved in water, that last compound when dissolved in water, how many ions we will get?
Only one ion.
Huh?
Only
Is that
one
ion,
ion,
first
sir.
of all? Is that ion, first of all? Is that box has any positive or negative charge?
No, sir. No, sir.
After dissolving in water?
No, sir.
Huh?
No, sir.
No. CO, NH3, thrice Cl3. It is not an ion. Am I correct?
Yes, sir.
That means no ions are here. In solution, no ions are here. Clear?
Yes, sir.
Now, through these aqueous solutions, when current is passed, when electricity is passed, where more conductivity we can exploit, we can expect. Where more conductivity we can expect. Conductivity. Conductivity is directly proportional to the conductivity is directly proportional to number of ions.
Yes, sir.
Okay, now. So let us take this one as first complex, second complex, third complex, fourth complex. See here, conductivity, nothing but electrical conductivity, my dear. Electrical conductivity directly proportional to number of ions. No ion, it is a non-conductor, my dear. Okay, now, therefore, 1, 2, 3 are conductors. Am I correct or wrong?
Yes, sir.
Because those have ions. Fourth one, conductor or bad conductor? Fourth
Bad
one, ions
conductor.
are there or not?
No, sir.
So it is a non-conductor. Clear? If ions are there, there is conductor. If no ions are there, there is bad conductor or non-conductor, which is insulator, not carrying current through them.
Yes,
So
sir.
current carrying capacity is directly proportional to number of ions. No ions are there, there should not be a conductor. Now, order of conductivity, my dear. Order of electrical conductivity. Tell me, what is the order? Which one is good conductor?
1
One,
greater
two,
than
three,
2.
four. Huh?
1 greater than 2 greater than 3.
Yes. 1 greater than, 2 greater than, 3 greater than 4. Correct? That is order of conductivity. See, my dear, in practicals, already you learned Cl minus ions are identified by using AgCl, a silver nitrate test. Am I correct? When silver nitrate is added, the Cl minus ion precipitated as AgCl. Clear?
Yes,
Cl
sir.
minus ion. Okay. See, if this is treated with AgNO3, how many AgCl precipitates out? How many AgCl? How many moles of AgCl will precipitate? It is in excess. It is in excess. How many moles of AgCl? How many moles of Cl outside? 3. Therefore, 3 moles AgCl is precipitate. AgCl white in color, my dear. Well, how many moles of white precipitate is formed?
3 moles.
First, 3 moles. So here, 2 moles AgCl is there. So to this, excess of AgNO3 is added. How many moles of AgCl white precipitate is formed?
2.
2 moles AgCl white precipitate is formed. Correct. If this is dissolved, if this is treated with AgNO3, how many moles of AgCl is formed? 1 mole, 1 mole, 2 mole, here 3 moles. So it is a precipitate, white in color. What is the color of AgCl? White colored. Now, if this is treated with AgNO3, that is treated with AgNO3, how many moles of AgCl is precipitate? Tell me your answer.
0.
0. No precipitation. No white precipitate. Correct?
Yes, sir.
Did you understand the concepts?
Yes, sir.
See here, if outside is Br minus R, it is yellow, AgBr are formed. Okay, na? If outside Br minus AgBr, if outside is I minus AgI is formed. Clear? Based
Yes,
on
sir.
nature. See here, AgCl, white in color, white precipitate, my dear. AgBr, light yellow precipitate, pale yellow precipitate. AgI, yellow precipitate. So number of times he asked yellow precipitate is formed or white precipitate is formed like that. How many moles of yellow precipitate? How many moles of white precipitate? Like that he asked a number of times in your objectives, right? So these are the situations. Clear?
Yes, sir.
Okay. So next, for example, if outside SO4 minus ion is there, for example, if outside SO4 minus 2 ion is there, not here, but if it exists, that is treated with BaCl2 tested. It gives BaSO4, barium sulfate. One sulfate ion outside, one mole barium sulfate. That is white precipitate is formed. So depending on outside ions present in the complex, we can test with different reagents. If halide ion is there, that is tested with AgNO3. If sulfate ion is there, that is tested with BaCl2. Clear? If sulfate ion is outside, That is tested with BaCl2. Okay, na?
Yes, sir.
Clear? Ah?
Clear, sir.
So this is very, very, very important towards your objective side on your boards. Okay. Now, Werner, draw some the structures of these complexes, my dear. That is, it is CONH3 6 times outside Cl. See, my dear, I am drawing the structure of this one. There is a cobalt which is in plus 3. Correct or wrong?
Yes, sir.
Cobalt plus 3. How many ammonias are there?
6.
So are these with coordinate covalent bond or ionic bond?
Coordinate bond.
So that's why. So NaH3 with coordinate covalent bond indicated with solid line, thick line. Okay. So 6 ammonias, 6 solid lines. Okay. These are, that means, are these ionizable or non-ionizable? Tell me. Are these break down into ions or not?
No, sir.
No. How many Cl minus outside?
3, sir.
Those are ionizable or not?
Yes,
Yes,
sir.
sir.
So that means ionizable valency is indicated with dotted lines, Cl minus. This is the Werner structure for above complex. Okay, na? So by seeing the structure, which is ionizable, which is not ionizable, we can identify easily. Clear?
Yes, sir.
Those dotted lines are easily break down into respective ions, but solid lines cannot be. Okay. Number of solid lines around cobalt plus 3. How many? How many solid lines are there? Around CO plus 3?
6.
6. That is coordination number. Coordination number is equal to 6. How many dotted lines are there?
3, sir. 3.
That is the primary valency. Clear? Solid
Yes.
lines are secondary valency. Dotted lines are primary valency. See here, I am drawing this structure. Here also, cobalt is in plus 3 oxygen stage. How many ammonias are there? How many ammonias?
4, 5.
5. That means 5 solid lines. Because these cannot be ionizable. Okay, na? These satisfies only secondary valency. Ammonia only satisfies secondary valency. Inside, how many chlorines are there?
God. 1 chlorine.
Huh?
1
One
chlorine.
chlorine. That can also satisfy primary valency. Am I correct or wrong?
Yes, sir.
Sorry, secondary valency.
Yes, sir.
Okay, na? So now how many solid lines?
5, sir. 6 total.
6. Total 6, no doubt. But 5 with ammonia, 1 with chlorine. Okay, na?
Yes, sir.
Now coordination number how much? 6. Now, how many chlorines outside?
2 chlorine, sir.
Outside chlorines.
2, sir.
Outside chlorines, how many?
2, sir.
In this structure, outside chlorines, how many are
2,
there?
sir. 2, sir.
2. That means those 2 chlorines satisfies only primary valency. Cl minus. Cl minus, correct? Are they are they satisfies primary secondary valency or primary valency?
Only primary values.
Primary. But this chlorine satisfies both primary valency and secondary valency. Am I correct?
Yes, sir.
So that's why this chlorine has also dotted line. That means one chlorine satisfies primary valency as well as secondary valency. That means one chlorine acts as both ligand as well as ordinary ion. Correct or wrong? Ligand means solid line. RD ion means normal dotted line. So that has both solid line and dotted line. Therefore, that satisfies both primary valency as well as secondary valency. See, my dear, in this structure, how many chlorine satisfies both primary and secondary valency?
Only one, sir.
Only one. Like that here, how many?
First one.
Huh? How many chlorine satisfies both primary valency and secondary valency?
2 chlorines.
How many satisfies only primary valency?
One.
One. How many chlorine satisfies both primary valency and secondary valency in this case?
3, sir.
How many only
Inside,
primary
zero.
valency?
No, sir. 0, sir. Primary valence is 0.
Only primary valency zero, but both primary and secondary valency,
Uh, Only secondary valence, you know, sir.
the number of chlorines which are inside the square brackets satisfies both
Primary and
secondary
secondary.
valency.
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Now, how many chlorines satisfies both primary and secondary valency?
3, sir.
Three. How many only primary?
0, sir.
So now I'm drawing a structure for this one. See here, cobalt plus 3. 3 ammonias, my dear, NH3. Okay. 3 chlorines. Satisfies here primary valency and also satisfies secondary valency. There is a dotted lines we can also draw. Clear? That last structure corresponds to which one? 1, 2, 3, 4 compounds. Among 1, 2, 3, 4 compounds, that last structure corresponds to
CO and H3 taken things here.
among these 4, this structure corresponds to 1, 2, 3, 4.
4, sir.
Fourth one, correct or wrong?
Yes, sir.
Fourth one. Okay. You can draw this structure. You can draw this one structure
Yes, sir.
on your paper. Now, Shiva, where are you? Rajmundry?
No, sir.
Huh?
No, sir. No, sir. Rajamani, sir.
Okay. Now tell me. Draw the structure of this one. Completed.
Yes, sir. Dark lines
Okay.
is NH3 4, sir. Thick lines.
CO plus 3. Thick lines 4 are
No, sir.
6
NH.
ammonia. 3 or 4 ammonias.
Yes, sir. Thick line
4
dotted
ammonias.
line. 2
1
chlorines,
chlorine.
yes, sir.
1 chlorine.
Yes, sir.
1 chlorine outside. That means only dotted line. These 2 chlorines has both dotted lines and thick lines. Correct?
Yes, sir.
Sir, I have a doubt, sir.
Am I correct? Yes.
Sir, a dotted line, thick line, రెండు ఒకదానికి ఎలా పెడతారు?
Because chlorine satisfies primary valency or not? Is this satisfies its positive charge or not?
Yes, sir.
So that is a dotted line.
Okay, sir.
Is this donates electron pair to the central metal atom or not?
Correct, sir.
Electron pair, because chlorine has 3 lone pairs. 1 lone pair can donate.
Okay, sir.
Clear?
Clear, sir.
Okay. So this is the Werner's coordination theory, boys. Why some ions are coming out from the complex? Why not someone? That is explained on the basis of 2 different valency, primary valency and secondary valency. Okay. Clear? Now, my dear. In these complexes, generally, a box ion is formed by the combination of metal and ligand, correct? This box ion. This is breakdown as CONH3 6 times plus 3 ion, 3 Cl minus ions, correct enough? When dissolved in water.
Yes, sir.
So, okay. Is this ionizable or non-ionizable?
Ionizable.
Is this ionizable or non-ionizable?
Inside.
Ionizable means, I mean, break down into ions.
No, sir.
Ionizable means break down into ions. Is this ionizable or not?
No, sir.
No. Okay, now this box ion is called as a complex entity. The name of this one is complex entity, non-ionizable part. So how a complex entity is formed? Complex entity is formed by the combination of metal atom or metal ion along with ligands. Okay, now metal atom or metal ion, along with ligands. That combination gives complex entity. Clear?
Yes, sir.
So now we can identify what is the structure of this complex entity that is explained on the basis of VBT and CFT later cases. Okay,
Yes, sir.
complex entity. So this is Werner's coordination theory, my dear. So Werner's coordination theory clearly explains how a complex is formed, why some ions are coming out or why not some ions. Okay, so their conductivities, those are clearly expressed, but not expressed stability of these compounds. No doubt, complexes are very stable. Why those complexes are stable? Not explained by this Werner theory. So complexes have some colors. Why complexes have colors? Not explained. Magnetic property is not explained. Only the explained part is how they are formed, what is their conductivity. That is explained on the basis of Werner theory. Later, that stability and the stability is explained on the basis of EAN rule, effective atomic number rule, that we will discuss tomorrow. Okay.
Yes, sir.